Good afternoon. Today, our team, consisting of George Hani, Philippatir Romani, Mohammed Ehab, and Paula Nasser, is proud to present our CAD assembly and analysis of the N32-125 centrifugal pump. We chose this specific project because centrifugal pumps are the backbone of modern industry, used in everything from water supply to chemical processing. From a design perspective, it offered the perfect level of complexity to showcase advanced SolidWorks skills, including sub-assemblies, motion studies, and structural simulations. Our design process followed a rigorous 6-step workflow, starting with research into N32-125 standards, followed by individual part modeling, full assembly mating, and finally, simulation and documentation. The final assembly is a substantial piece of engineering. Total mass, approximately 48 kilograms. Complexity, 16 custom model parts, supplemented by standard DIN components from the SolidWorks library. Key features, a cast iron volute casing, a 6-blade impeller, and a 35mm steel shaft. Modular design, we utilized a modular architecture, meaning the coupling, seals, and bearings can be serviced independently, a critical feature for its 7-year design lifespan. As you can see in our motion study, the pump operates through a clear mechanical sequence. An electric motor drives the 35mm shaft via a flexible sleeve hub coupling. As the shaft rotates the impeller, it creates low pressure at the eye, drawing fluid in and accelerating it radially through centrifugal force. In SolidWorks, we verified this using concentric, coincident, and angular mates. The simulation applies motor torque as the driving force, ensuring all components, from the packing gland to the radial ball bearings, maintain perfect alignment during a full 360-degree rotation. To visualize the spatial relationships, our exploded view follows the actual assembly sequence. It begins with the welded steel base plate. We then mount the motor and bearing supports. The rotating core, the shaft, bearings, and 6-blade impeller is then aligned. Finally, we seal the system with the lantern ring and packing gland before securing the volute casing and protection guards. Structural integrity was validated through static stress analysis. The shaft, analyzed for torsional loads, we found a max von Mises stress of 51.21 megapascals. With a material yield strength of 620.4 megapascals, the shaft has a safety factor greater than 12. The casing, under an internal pressure of 50 psi, the casing experienced a max stress of 21.15 megapascals, maintaining a safety factor of over 10. Beyond mechanics, we performed a sustainability LCA. We evaluated the carbon footprint, energy consumption, and end-of-life water eutrophication to ensure our material choices were as environmentally responsible as they are structurally sound. In conclusion, our N32-125 pump design meets all industrial standards for performance and maintenance. By utilizing standard DIN fasteners and ensuring high safety factors, we have developed a robust, reliable, and sustainable industrial solution. Thank you for your time.